The video at the upper left should be familiar to you. It's shown in the title slide of each of these lectures. The reason that it's there is it's a fascinating example of how the reflectance of an object can vary as you change your perspective when the object is illuminated by coherent or partially coherent illumination. In this case, it's a spatial light modulator that's being illuminated by a laser source. You can see speckle in the reflection from the edges of the device. As the device rotates, you see the reflectance flashes on and off. That indicates internal structure inside of the device. We want to understand how we could use that to characterize the object in more detail. This particular video was recorded by Greg Nero and Gordon Hageman, who are shown in a couple of the images shown here. Also shown is Ahmed Algami, who worked with Gordon and Greg in recording spectral reflectance over a long range. This is another picture taken by Greg. This was a set of 9 helicopters flying over Tucson, and as the helicopters fly, you can see that their reflectance flashes on and off, again reflecting the change in the observed image from different perspectives. This change in the observed image from different perspectives is not predicted by incoherent imaging. You have to explain it by understanding the nature of specular reflectance. And here, as you zoom in on part C over on the right, you can see the helicopters have this hemispherical dome on the front that causes their reflection to change under sunlight illumination as you look at them from different perspectives. So Gordon and Greg and Ahmed went out and captured reflectance over some range. Here we're looking at a range of 27 kilometers from one side of Tucson, Arizona to another. You see the object, which was on a rest stop on the road up to Mount Lemmon on the left, and a telescope which was on Sentinel Peak near downtown Tucson, looking across the valley at this reflected object. Here's what the range looked like on a map from Sentinel Peak over here, over to the road up Mount Lemmon over here. So they put objects that look like this. These are metal reflectors that were approximately 20 millimeters on a side with various shapes, and rotated them as they observed them under the telescope. And you see that they were not able to resolve the object, but they did get some interesting reflected patterns from the objects. As they rotate, you see video like this, so that you see flashes as the object's position is turned, and the pattern of the flashes, we can look at the total reflected power coming from the object here, plotted as a function of the frame number, but that corresponds to the angle of the object. And you see this characteristic structure. That structure indicates something about the surface normals of the object. So it's not related to the image resolution. The sunlight that's illuminating the object has a fixed direction and is not modulating the reflected signal. But in this sort of flash pattern we get as we look at the object from different perspectives, we can say something about the surface characteristics of the object, even though the object is unresolved. Here's a plot in more detail showing those different surface structures. And here the object was rotated one way and then the other, so you see this anti-symmetry as the object is rotated in the forward direction and then rotated in the backward direction. So let's try to understand how this works. Computational imaging. Episode 54, Radiance Tomography. Up to this point in our discussion of incoherent imaging, we assume that the object is an incoherent radiator. Then we image the irradiance or the mutual intensity generated by the object in the focal plane of a lens. But of course, the object could be partially coherent. Typically, the way that the object would be partially coherent is it's illuminated by partially coherent illumination, such as sunlight. And so the sunlight has a angular divergence of delta theta, and as we've seen, a source with a finite angular range corresponds to a partially coherent source. And so the reflection off the object also would have some angular range, reflecting both the characteristics of the object and its illumination, and that would create a situation where the field at the object is partially coherent. We can use the same modeling techniques as we've used for other fields to describe this situation. The mutual intensity in the plane of the object would be the illuminating mutual intensity multiplying the reflectance of the object in each of the object variables. So here this delta x would be x prime minus x double prime in the plane of the object. We'd use the coherent impulse response in each of the x prime, x double prime variables, integrate over that, and we could get either the cross-spectral density or the irradiance in the plane of the focus of the remote target using the standard tools that we've used. So we have kind of a very simple way to model this once we've assumed a certain object reflectance, and if we know the illuminating mutual intensity. We've seen that for sunlight, for example, the mutual intensity is the Fourier transform of the source. And for sunlight, which we have a circular disk, that would be this Jink function multiplied by the spectrum, the power spectrum of the source. The angular extent of sunlight is 0.0083 radians, which means its cross-sectional area is going to be something like the wavelength divided by this angular extent, which would be around a couple hundred wavelengths. So let's look at this transformation between the object reflectance and the irradiance on a partially coherent illumination for the case of a focal imaging system. So in this case, our coherent impulse response, H, is going to be our focal impulse response, which is the Fourier transform of the pupil, as we've seen. Here's this H sub r, Fourier transform of the pupil, and then we also have the phase terms that we used in tychographic imaging. So the quadratic phase terms, which we've reduced here in terms of this delta x, where delta x corresponds to the separation of the source points in the object plane, and x bar is the mean position of the source points in the object plane. F is the reflectance in the object plane, which we've evaluated at x1 and x2, but we've written that as x bar plus delta x and x bar minus delta x, and we're modulating that by the the mutual intensity W of delta x. Delta here is the same delta we used back in tychographic imaging. It's the shift of the observing position of the camera. So now, in contrast with incoherent imaging, where the only thing that would happen if we move the camera is that the image will shift, which we get in this shift in the impulse response, m delta here. In the case of a partially coherent illuminated source, a shift in the camera position can lead to a phase modulation in the observed image from these quadratic phase terms. As an example, let's consider imaging of 2 point sources with partially coherent illumination. So at the top here, we're showing the general transformation between an object distribution f of x1 and x2, where we've written x1 is x bar plus delta x over 2, and x2 is x bar minus delta x over 2. So x bar here is the mean position of the object, and delta x is separation between two object points. We're observing the camera image at g of x and delta. X is the position in the image plane of the camera, and delta is the mean position of the camera. So we're moving the camera laterally, the same as we did in Fourier tychography back in chapter 6. We have that quadratic phase term that modulates the phase of the observed image or of the impulse response as we shift the camera at the front of our integral there, and then we have our coherent impulse response corresponding to the Fourier transform of the pupil in the form of HR. Okay, now if we substitute in that f of x is equal to delta at x1 and x2, we get images at x1 and x2 as shown at the bottom here. So we get an image W naught, the in irradiance of the illumination at x1 and W naught at x2, but then we have a cross term W of delta x times the cross product of the two impulse responses at the bottom, because because the field is partially coherent in the observed image, we can see interference between the images of the 2 points. So we can now assume that the points are close enough that the impulse responses overlap in image space, and so we've taken out this we've taken out h of x plus or minus delta x because we're assuming that the images of the 2 points overlap. So here's our 2 points. We have a lens, and then in the image space, each of the points creates an impulse response, but the 2 points are separated by a small enough distance that the impulse responses are really indistinguishable, and so that we've taken out, they create the same impulse response. Both of them create an impulse response of their self-image, and then we have the cross term from their interference. And it's the same as we saw for ptychography. We see a beat as we move the camera laterally. The relative phase of these 2 points shifts, and we can see a beat that would allow us to create a synthetic aperture and resolve the 2 points, even if they're not resolved in the image plane. Now, to do that, the 2 points have to lie within the coherence cross-section of the source. So in the case of a ptychographic system where we assume a fully coherent illumination, the coherence cross-section was unbounded, and so this term would be 1. But now we see that for a partially coherent source, we could see that this kind of beat as long as the 2 points lie within the cross-section of the coherence. So for a sunlight, that would be, a couple hundred wavelengths, a couple hundred microns, and we'd see this beat. If we had a small source like an LED, it's going to have a small angular range, and so even for a incoherent LED, we would see this beat as we move the camera, which opens the door to all kinds of new ways to think about how to use imaging systems and how to use ptychography in systems that may seem incoherent. Now, of course, with sunlight, as we saw, we see dramatic effects as we move the source, but those effects can't be due to like this beat frequency because we're not really going to resolve 200 micron objects from a great distance with sunlight. But we do see dramatic changes in the overall brightness of the sources as we change our viewing position. So let's go back to our general transformation between a remote reflector illuminated with partially coherent illumination and our image that we observe at position x with mean camera position delta. So here's our object, and here's our illumination coming, has some mutual intensity W of delta x, and we're going to observe it here at some camera position, or image position x with camera position delta. So let's assume that x is observing a point x1 or x2 in object space, but we'll assume that W of delta x is smaller than the impulse response. So we're not able to observe this kind of beat frequency because the impulse response as observed on the image is much broader than our coherence cross section, which would be, a couple hundred microns, let's say, and on our ground sample distance, the area covered by 1 pixel on the object, let's say, could be millimeters or centimeters if the object is far away. So it's much bigger than W of delta x. So we can assume that over the range of which W of delta x is non-zero, h, the impulse response, is constant. So then if we integrate with respect to delta x as shown here, we're basically taking the Fourier transform of W with this phase term over delta x. Now there's something to remember. If we go back and look at our form of W of delta x, we've said that W of delta x is the Fourier transform of the source power spectral density. So if this source is spatially incoherent, the mutual intensity that we see on the object is its Fourier transform, and we saw that had the form of like a jink. But it also has this phase term. So W actually is directional. It has a e to the I k dot r and then times W of delta x. Because if we shift s, if we shift this, that would cause a phase term in delta x and delta y, and we already have a phase term in z. So the W is a directional term. So when we take its Fourier transform, we're basically going to vary this phase term. And the reason for that is that W comes here and gets reflected in some direction. So we're basically looking at how much of the incident light is reflected in the direction of the source. Now, if f of x is equal to 1, then we're going to integrate basically over given the direction of W, we're going to integrate the full area of the cross section, and so we'll get a brightness, which would be the integral over the coherent patch. Now, in contrast, if f of x was random, then we integrate basically only over the correlation length of f of x. So, for example, if we had a spatially random source, and let's say it has correlation length of around 1 wavelength, then the integral of over the patch of coherence would be proportional to that area of one wavelength when we look at the reflected signal. In contrast, if we have a f equal to 1 and we integrate over the area of W delta x, even if W of delta x is a couple hundred wavelengths, that would be the area squared, so like 10,000 times brighter than the reflection you would get off of a incoherent source, which is why if you see sunlight reflected off of a mirror or glass, it's going to be brighter by a factor of the area of the coherence area than if you see it reflected off of a diffuse surface. So the relative brightness of it reflected off of a mirror versus reflected off of a diffuse reflector should be around 10,000. This idea that W is directional is reflected in our definition of the radiance of the source. So if we take that term that we just saw of the Fourier transform of W, which is what we're going to observe when we observe an incoherent imaging system, that term is the radiance. So this is the energy in the field at point X propagating in direction S here at frequency nu. So now the field on the surface of the object, instead of just the density of the energy density of the field at point X becomes the energy density propagating in a certain direction. This is our definition of the radiance of the source. And an incoherent imaging system now observes the radiance propagating in the direction of that image rather than observing just the incoherent reflectance of the source, the incoherent emittance of the source. So in general, the problem is defined by this idea of the BRDF, the bidirectional reflection function of the source. So if you illuminate a source from a certain direction, the source is going to reflect differently in different directions. That defines the radiance from that point at the source, and so the general problem of imaging becomes from the image that we see of the source remotely, reconstructing the reflectance in a certain direction at each point in the source. So the source, instead of being three-dimensional, is now five-dimensional. Every point in 3 dimensions could emit a field propagating defined by a direction on the surface normal. So the source radiance, or the source radiance, is the field emitted in direction x over f at position x as a function of frequency. And if we include, time and spectra, this becomes a 7-dimensional imaging problem using still resolved with the incoherent impulse response. This problem of reconstructing the direction of the reflection at different points in space is the problem that we started today's discussion with, and we did see that we could see characteristic reflection patterns from points on the surface. It's a very deep and interesting and challenging area that just shows the richness of computational imaging, that in principle we could look out and cross the valley like we saw in the last episode and try to understand the directional reflection of different points on the source and identify those targets without being able to fully resolve them. We're not going to have enough time, to consider all the details of radiance tomography, but hopefully you understand the mathematical tools that we could use to analyze it from this section and understand the full richness of the problem. In computational imaging, everything comes down to building a model for the relationship between the object and the field, building the forward model, and then figuring out how to invert it. But it's time for us to move on. We're going to move into Chapter 9, where we're going to talk about how to discretely model the fields that we've described by these continuous coherence functions in the last two chapters. With the next episode, we're going to talk about pixelated diffection systems and how we develop a system transfer function in the context of a pixelated system. Here we see a picture of a Sony charge-coupled device from Wikipedia. The color you see on the device is, of course, comes from the grading behavior of the pixelated structure of the source is now diffracting and creating observed color under white light illumination for this focal plane array. So let's talk about the impact of that on imaging systems in our next episode.